Hi guys, welcome to my channel. In this video we are going to solve a questions about reinforced concrete course, and the question is a beam, and now we can see there is a cross section is shown in the figure. So let's solve the question. First we have to make an assumption that we are going to write as the compression steel has yielded. And now you can see there are three forces: and tension steel, compression steel, and compression concrete. And so we have three forces, and these two will be to the left side, and this is going to be the right side. Okay. So now the assumption is that due to this assumption, we are going to obtain a neutral axis is C, and we have also an A is the concrete, the effect of the concrete depth. Okay, effective concrete depth. So now let's solve the question. I'm going to write an equilibrium like that. Equilibrium like this. It's going to be CC plus CS equal to TS. Okay. Now, due to this equilibrium, I'm going to obtain a C value. Okay. So let's write it. 0.85. Now I'm write the CC. Okay. 0.85 multiplied with FCD. What is FCD? The design strength of the concrete. Okay. So this is 20 megapascal multiplied with 300 is BW. This is BW. Here is BW. Okay. And multiplied A. A is this concrete effect of the concrete. Okay. This is this A. A is equal to also K1 multiplied C. K depends on concrete, type of concrete. Okay. And now in this question is K1 is equal to 0.85. And now multiplied with A, we write. So, and we are going to take as plus. Now we assume that the compression steel has yielded. Okay. The assumption first is this. So what is CS? CS is going to be something like that. The area of steel at this steel. Yeah, okay. The area of this. I'm going to write here 763,407 multiplied with, if it is yielded, what is FYD? What is FYD? FYD is the design strength of the steel that we use. So it's going to be 365.22, okay, and equal to the TS. What is TS? TS is the area of steel, the bottom steel. What is area of steel? 1900.663 multiplied with the FYD. So FYD, what is FYD? The design strength of the steel of the bottom steel. It is both the same. You can see 420, if you remember, 420 over 1.15 FYD equal to 365.22. okay, it comes from here, so you know it. I didn't need to write it. So 365.22, and from this equation I'm going to obtain A value as 81.44 millimeter. Okay. And if you know that I told before, A is equal to K1 multiplied C. So, and K is 0.85. So I'm going to obtain a C here, 95.8112 millimeter. Sorry, 812 millimeter. Okay. So now I have the C value. So now I'm going to take the similarity of the triangular. So I'm going to obtain the yield point of the steels. Okay, this is the yield point of the steel, the top steel. This is for the yield point of the bottom steel, and this is yield point of the concrete. Okay, so I'm going to write an ratio like that. I'm going to make a compatibility. Excuse me. I'm gonna take this one to here. It's going to be better to make the solution. For now, let's look at here. ES prime, okay, epsilon S prime over this length, right? And UCU, yeah, epsilon CU over this length, CU. So I'm gonna write here epsilon S prime over 95.812, this is C, minus 35. What is 35? It is D prime, so rust cover, right? This is rust cover, equal to 0.003. What is that? This is the yield point of the concrete, and over C value. Let's repeat it. I told you that before. I'm going to take the epsilon S prime over this ratio. Okay, this ratio. I can show you like this ratio. And epsilon CU, okay, CU, I'm going to take to this ratio. So this is going to be epsilon CU over C, and this is going to be epsilon C prime divided C minus D prime. This is D prime, this length. This is rust cover, okay? So from here, now I'm going to obtain the yield point of compression steel as 0.001904. You know, normally the yield point of the steel ESY is equal to 0.001825. Okay, when I compare with this, and I know that it's bigger than epsilon SY, so the compression steel has yielded. Now I obtained the compression steel has yielded. So let's check if it is tension controlled or not. So the bottom steel is yielded or not also. So how it's going to be? It's again the same from the triangle, the similarity of the triangular. This ES, I'm going to show you here. This ES, I'm going to divide it to UCU. Okay. I'm going to divide this length to this length. So let's write it. Epsilon S over 465 minus 95.812 equal to 0.003 over 95.812. This is C, and this is D, this is minus C, okay? From this equation, I'm going to obtain epsilon S 0.0115, and it is greater than epsilon SY, the yield point of the steel, 0.01825. So it is tension controlled. Okay, now the first part I solved, so let's solve the second part. For the second part, it asks to find the balanced steel area. Balanced steel area. How is it going to be found? It's going to be found like that. I'm going to make the same compatibility, and I'm going to obtain it. So now I don't know the neutral axis. What is neutral? I told you that at the beginning of the question. The neutral axis is C, okay? But now I need to find the CB. Now I need to find the CB. So I'm just going to deal with this one, because I assume that epsilon S prime is yielded. Okay, so let's find it. It's going to be, I'm going to assume that this steel also yielded 0.001825. The yield point of that I'm going to take as a reference. Over what is D? D is the length from that point until that point. 465 minus, what is CB? I don't know what is CB. So then the yield point of the concrete over CB. Okay, this over this over this, and this over this. So from this equation, I'm going to obtain a CB 289.119 millimeter, and A, if I need a balance, will be equal to 245.751 millimeter. So now I have AB and CB. These are my the things that I need to write in equilibrium. Okay, so let's write equilibrium. The equilibrium will be written like that. These are the forces again. So for the equilibrium, it's going to be written as CC plus CS equal to TS. Okay, so what is CC? 0.85 multiplied with design strength of the concrete is 20 megapascal, and multiplied with 300 is BW. It never changed the short length of the beam, the bottom length. Okay, and multiplied with A. What is A? What is A? 245.751 AB. Okay, now I define it here. Plus AS prime. What is AS prime? This the area of the area of the steel, the first steel, the top steel. So 763. Okay, 763 point. Let's check. 407 multiplied with. We assume that it's also yielded. Okay, it's yielded. If it is yielded, so 365.22 is going to be the design strength of the steel. Okay, so ASB, we don't know the balance steel area for the bottom steel. Okay, for the tension steel. So multiplied with what? With 365.22. Why? Because we assume that for here, this is, look at here, this is epsilon S. Okay, so that means that we assume that it is yielded. If it is yielded, you are going to write as 365.22 for S420. Okay, so and from this equation, I'm going to obtain as the balanced steel area is 4,195.123 millimeter square. Okay, this is ASB, the balanced steel area. I'm going to make a compare. Okay, the normal steel area now is used. Okay, if it is smaller than the balanced steel area, so it is under reinforced. Normally we want the section will be under reinforced. If it is over reinforced, so it's critical, we don't want it. So it is under reinforced. Now we find the balanced steel area also. Let's solve the third part. What is third part? Third part, it asks us determine the ratio of steel. So the rho and rho prime, rho balance, rho mean, and rho max. So let's find them also. The third part, I'm going to obtain the rho for the bottom steel. Okay, it's going to be AS over BW multiplied with D. So what is that? 1900.663 over 300. This is the BW multiplied with 465. That will be equal to 0.0136. Okay. So let's find the rho prime, the top steel. Okay, the ratio of the steel. It's going to be AS prime over BW multiplied with D equal to 763.407, okay, over 300 multiplied with 465. So this is also be 0.00547. So let's find the balance steel balance ratio. It's going to be PB. So I'm going to write ASB over BW multiplied with V. It's also 4195.123. Sorry. This will be 300 multiplied with 465, and it's going to be 0.03. And here now I'm going to obtain the raw mean, the minimum, the ratio of steel that has to be in the section. 0.8 multiplied FCTD. What is FCTD? I wrote it in the question. And FYD. So it's also will be equal to, let's write, and I'm going to write the whole equation. FCTD 1.3. So let's write here 0.8 multiplied 1.3 over FYD. So 365.22 will be equal to 0.0028. Now that's enough. So let's find the raw max. For the raw max, then we are going to make a compare, and this part will be finished. So for raw max, it's going to be equal to 0.85 multiplied with raw balance. So 0.85 multiplied with what is raw balance? Raw balance is 0.03, and it's going to be equal 0.0255. Okay, now this is the raw max. So let's make a compare. The ratio of steel must be smaller than the raw max. So the normal raw, the bottom of steel, okay, will be smaller than or equal to raw max. Now you can see the raw is 0.0 here is 0.0136, and raw max is 0.0255. So it is smaller than, right? So if it is smaller than, we are going to understand that. So it is under reinforced. Okay. So now we solved the third part. So let's solve the fourth part. At the fourth part, it asks MR. What is MR? The moment can be carried by this section. Okay? The moment can be carried by this section. The fourth, right? Let's write it here. MR, it asks. So let's find it. I am going to write like that. I'm going to take these two forces, okay, respect to that point. So MR will be equal to CC multiplied with D minus A over 2, okay, and plus CS multiplied with the length of the length from here. I'm gonna show you. For example, this is the force it acts, the point, the point that the force will act. So I'm going to take this, subtract the rust cover from here. So it's going to be 465 minus 35. It's going to be 430, right? So this will also be d minus d prime. And now we are going to obtain the moment from this equation. So this d minus a over 2, I'm going to show you here also how it's going to be. For example, now I'm going to take the moment with respect to here, and this is at the center of this block CC, okay? So how it's going to apply it? It's going to take the half of this a, right? So I'm gonna have from that point until that point as d, as the length, okay? D minus a over 2. This is going to be the moment arm for CC, okay? For CS, I'm going to take the moment with respect to that point. For the CS, it's going to be something like this. It's going to be, for example, this is a rust cover here, D prime, okay? So, and this is also D prime. Normally it is 500 millimeters, so I'm going to take the 2D prime. So it's going to be 430, okay? This is going to be 430. So let's write it. I'm going to write it first here. Okay. So 0.85 multiplied with the design strength of the concrete, multiplied with 300, and multiplied with also A. What is A? Sorry, what is A? A is here. A is, I obtained at the first A. Sorry, I'm gonna have to find it. 81.44, okay? 81.44, and multiplied with the moment arm. What is moment arm here? The moment arm here is 465 minus 81.44 over 2 plus CS. What is CS? CS is, it's yielded, so I'm going to multiply with 736.407, the steel area of the top steel, okay? Multiplied with 365.22 and multiplied the moment arm. What is moment arm? What was D? D was a 465 minus also D prime. What was that? 35. So I'm gonna obtain the moment here. Now this is the moment can be carried by this cross section of the beam. Now we obtain our moments. So let's make a compare with the section 5. Sorry, the part 5. Okay. Check if it is okay or not for the ultimate moment of beam of given 4-meter length. Okay. So we are going to assume that. Let's write it here. Okay. For the part 5th. For the part 5th, I'm going to write here. For the part 5th. We are going to assume here this our beam has a span as 4 meter and it has loads also, as dead load is 15 kilonewton meter, okay, and live load also 10 kilonewton meter. So the design load will be used, you know, PD is equal to 1.4 multiplied with dead load and plus 1.6 multiplied with live load. So 1.4 multiplied with 15 plus 1.6 multiplied with 10 will be equal to 37 kilonewton meter. This is our load. So we have a load here as 37 kilonewton meter. The question is that, so we're going to calculate the moment here. What is MU? MU is equal to the moment at the span, WL square over 8. WL square over 8 will be equal to, what is W? 37 multiplied with 16 over 8. This is 4 square. The length is 4. Okay. So this is it will be divided 2, and I have 2 here. It's going to be 74 kilonewton meter. Okay. What is my MR? What is my MR? MR is equal to 296.111 kilonewton meter. It's greater than ultimate moment. Okay, it's greater than ultimate moment. What is ultimate moment? 74 kilonewton meter. So if the MR is greater than MU, ultimate moment, so that this section is okay, can carry this load. Okay, can carry this load. So the design is okay. Now the question is solved. Thank you for watching me. If you find anything wrong, please warn me. The comments, I'm going to revise them. See you for the next question.